Welcome, everyone. Welcome to our webinar on FMEA, using a spreadsheet to do an FMEA. I feel spreadsheets were one of the best things that ever happened to the FMEA process. I remember how easy it was when I started using a spreadsheet compared to the old paper forms we used to use. It really saved a lot of engineering time, and especially when you get into a natural iterative engineering process. I used a spreadsheet for many years. Then I learned that there are tools available. And lately I've been using tools, but today we're going to talk primarily about using a spreadsheet for FMEA. And then we're going to do a little comparison between the spreadsheet methodology and the tools. My name is Bill Goebel. I was one of the co-founders of Exida. I spent most of my career doing hardware design and engineering management. I wanted to let you know for sure that this is the 2023 webinar series, and we have 3 more to go after today. I hope you're able to tune into most of them, and I hope you get a lot of benefit from them, because that's why we're doing this. Exida was founded over 20 years ago by a number of technical geeks, and we're not salesmen or businessmen in any way, relatively speaking, but we're very intense, focused on technology. Exida is primarily working in the fields of functional safety, alarm management, and cybersecurity. And over the last 20 years, I'm quite proud that we have grown into a relatively large global company. One of the Exida groups does engineering tools. There are 2 suites available, the Excellentia suite, which is primarily a systems level design tool focused on process industries and machine safety. The OEMX suite is another set of tools focused on the embedded system and mechanical design and development process, which is primarily where FMEAs are done. Another Exida company does certification. Exida is an accredited body and a notified body in the European Union, and we are quite proud at how far we've grown in terms of our market impact in the world of functional safety and cybersecurity certification. I did tell you that we're kind of a technical geek company, and we're very proud that we've authored most of the industry references for automation safety, reliability, and cybersecurity. We don't want to keep all our knowledge secret. We want to do research and publish our research and share it with everybody in our books, our white papers, and our webinars, which is, I hope, we do a good job of doing that today. Failure mode and effects analysis. I learned the term back in the mid-'80s. And over the years, I've seen it evolve into multiple different things. So you have to be careful when you say FMEA. You can read the ASQ definition, American Society of Quality. But today we're focused on the design FMEA, and it is a design verification technique. What do we mean by that? We look at a design and we try to find problems, and if the problem is big enough, recommend mitigations to fix the design and make it better. Now, why do we do that? I mean, it takes some time to do an FMEA. Why bother, isn't it? Well, I should say, I never wanted to do an FMEA. I just wanted to get on with my design. But when I used to do that, I found problems much later in the development process. And it cost our project time and money because we had to rework. FMEA is a method to reduce rework, find problems early in the development process, and therefore save development cost and improve development schedule. The objectives of an FMEA. The obvious ones are we want to find problems in the design. I guess we should call them issues, not problems, but we start with a high-level architecture and typically go down through a hierarchical design, finding the problems at each level, which propagate to lower levels. And at the lowest level, we determine exactly what we're going to do to fix the problem. Now, there's a little more to it than that. We have to if we add requirements to a design to fix a problem, obviously we have to update the requirements document. While we're looking at the design, often we discover that we want to run an integration test. And while we're looking at the interaction between the architecture blocks of a design, it's the perfect time to define a good suite of integration tests. That's not common practice, but it is a very good practice and a way to save engineering hours later by doing things while you're in context. If you're doing an FMEDA, you can also provide important information necessary for an FMEDA. And one of my favorite topics, you can document your design and your design choices. You do have to generate a report explaining all this, but that is an objective of the exercise. And lastly, if you bring in new people, they can greatly benefit by understanding your designs and your design philosophy, and it helps training new staff members. And of course, we have to accomplish all this in the minimum number of engineering hours. So we have to be very careful how we do an FMEA, so we do not go over budget. FMEAs are often done at various design levels, and I just wanted to explain briefly what I meant about that. Often you will start at a high design level called a system, and the exida definition for system is the highest level of interest, because a system means very different things to different people. And you drop down through the hierarchical design, looking at the blocks, the functional blocks. And of course, a design will eventually go all the way down to a component level, mechanical or electronic or programmable electronic. It's all the same process. In some industries, the FMEAs go down to the component level, although that could suck up a lot of engineering hours, and it's primarily been replaced by the FMEDA technique, the component level analysis. Spreadsheets can be very complicated, depending on specific applications and additional objectives of the FMEA. I've seen them evolve into some things that were pretty time consuming, so you need to be careful about the complexity of your spreadsheet. A simple practical spreadsheet can accomplish most, if not all, of the objectives that we talked about. Of course, it can't accomplish some of the special application level objectives that are needed in some industries. But as an example of a simple practical spreadsheet, we could probably get away with 4 columns. You might be thinking, oh, no. In our company, we have 20 columns. Yeah, It's fair enough. I think it's fair to ask, do you need all that? What inputs does one need for an FMEA? You've got to have a description of the system. How does it work? And you often need a context drawing to have that understanding. How is this block, this thing, the highest level of interest, how is it connected to the outside world, mechanically or electrically, or both? You need failure modes of the system and a description of the failure modes. You need the architecture block diagram to the level you are analyzing and the functions of each block. If you start out not knowing this, not having documentation with this, or not having experts in the room who know all this, you're going to struggle with an FMEA. I think it's better to have the documentation myself because you need it eventually anyway, but your choice. Let's go through an example of using a spreadsheet. This is we'll call it a flasher device. It's a visible annunciation device used in safety systems, fire and gas systems, and even sometimes in security systems to warn people visually of a dangerous condition. In this case, the system being designed is this flasher. Now, I can easily imagine we have an existing design that we're going to redesign. It's often the case. And in this case, we're going to redesign using the existing mechanical properties so that our customers can use the new unit directly replaceable in the same mounting and everything else. But for FMEA, what we need to know is the function of this alarm dangerous condition annunciation device is to flash a light with intensity of greater than 500 lumens when the flasher input goes low. And it flashes once a second with a duty cycle of 50-50. Okay. What are the failure modes? Well, what it's supposed to do, correct operation, is when the flasher input goes low, the lights flash. Well, if the flasher input goes low and the lights do not flash, we can't enunciate the dangerous condition, so we're going to call that fail danger. If the input is high, and it should not be flashing, but if it does, we call that fail safe. It's failed. It's not doing what it's supposed to do, but it's enunciating when it shouldn't. That's in many industries called a false trip. But we'll call it fail safe. And when the input is high, the lights do not flash. That's correct operation. So what do we have here in terms of our inputs? Number one, we have a context diagram and a description of the function. Good. We have the system's level failure modes, fail safe and fail danger. All right. Good. Not quite there yet. I do appreciate the chart over here. It just makes things more clear. We have that as part of our description. We need the architecture block diagram. There's a power supply circuit which accepts, good descriptions here. We have the architecture block diagram, and we have descriptions of the functions of each block. Power supply block shall accept an input and supply voltages needed by the design transient voltage input protection. Okay, good. We can read the description of the flasher input circuit, the flash control circuit, and the LED arrays. I think we have everything we need to do an FMEA using a simple spreadsheet. Now, if you have experts in the room who've experienced a lot of power supply failures, they will quickly be able to give you some of the failure modes of a power supply, but they may not give you all of them. So often in a functional failure mode situation, we will use guide words. And the guide words, the whole concept came from a chemical industry analysis technique called a HAZOP. These guide words were transferred to the FMEA world back in the mid 80s. And you can see in the lower right-hand corner a chart of potential guide words and the chemical industry interpretation. But let's try to use those guide words for our functionality, our functional FMEA. Well, obviously, the first thing everyone thinks of is, I lose power. That's very common. Output goes to 0 volts. Well, what's the effect in the device level failure mode? Well, the flasher will not flash. Yep, that's for sure. It needs energy to light those LEDs. And that's clearly a fail danger. I think we're off to a good start. Hold it. Fail danger? I don't know. Maybe we have to do something about that. So let's go with the recommendation. We want in the 4th column. Let's sit down. What are we going to do? Well, gee, the input power fails. I mean, that's out of our control. If the circuitry of our own power supply fails, which is the focus right now, then let's sit down and brainstorm on some solutions to the problem. Maybe a diagnostic to detect when the power fails or the power supply conditioning circuits fail. If we just detect it after it fails and enunciate it so it gets repaired, maybe that's enough. And one of the members in the group says, hold it. If this is ever going to be sold into the fire and gas market, there's a standard which requires that we have redundant inputs with detection. So, sorry, we got to follow that standard. We want to sell into that market. And so we're going to list redundant power inputs required, and we're going to add a diagnostic to detect if either of the 2 power supply inputs fail. And those of you who have worked with redundant systems know how important it is for redundant systems to have diagnostics. A redundant system with no diagnostics is, well, I consider it to be a very weak, poor design. I'll use a stronger word than weak, poor design. So we're not going to do that. We're going to have redundant power inputs, power conditioning circuits, and diagnostics to detect if either circuit fails. Okay, good. Let's go down through the next guide word, more. What if the output goes too high? I don't know. Does that happen? I guess yeah, certainly could. Okay. What'll happen? Well, we expect the power conditioning circuit to blow a fuse because there's a transient protection. It said so in the specification. And if it goes too high, the transient protector will pull current and blow a fuse. Okay, maybe. What if it doesn't? What if the transient suppressor blows out before the fuse blows out? I think we better check this out in more detail. So we're going to define a test we want to make sure the transient suppressor will handle enough current to blow the fuse without disabling both of the redundant input circuits. That would be kind of a waste, wouldn't it? And we got to run a test to make sure. Okay, good. Hold it. One of the problems with FMEA is you forget these things. So we're going to go over to our action item application and enter an action item to make sure the overvoltage power, to add the overvoltage power test to the integration test plan. One of the biggest causes of development problems is just forgetting about things. And of course, an FMEA is not done to throw a report into a file and forget about it. An FMEA is done to improve the design so we don't discover all these problems later in the development process. Let's go to the next one. Less if the output is below specification. Well, we think if it's low enough, at some point there is a threshold, the flasher will not flash. That's fail danger. So, yeah, but we can solve that if we have redundant power inputs and if we have a diagnostic. You know, this seems like kind of a duplication. I'd rather keep it simple and change the first line. So we're going to cross off that and say output on the first line goes to 0 volts or below specification. I think that clears it up and gives us a much better and more detailed FMEA. And our recommendation is in place. Now let's go on. I couldn't think of anything for as well as, I don't want a switchable redundant power supply. We already have redundant power supplies. I don't need a switch or anything. Part of, only some. Well, we might have to, I don't know. I can't think of anything worthwhile on that. This is just too simple a circuit. Reverse. Uh-oh. A question pops up. Do we need protection for reverse polarity wiring? I mean, a lot of equipment these days, I mean, has that feature. And if customers make a mistake and burn up the flasher, I don't think they're going to be happy. I think we better put that in. And what happens? Well, the effect of that is the circuit will be damaged. I can just see some of the components burning out on the front end, fail danger. And so we're going to have a recommendation. We're going to add reverse polarity protection to the inputs on the power supply. I like that. The timing, and I can't think of any other failure modes that are relevant right now. So let's just move on. But I think we have to stop. Be careful. We have made a recommendation that redundant power inputs are required with a diagnostic. So that has to be added to our requirements document. And we have also recommended reverse polarity protection. That has to be added to the requirements document. We add that to our integration test procedure, and we've got to make sure we have action items so this stuff gets done. We got to go over to our requirements documentation system, and we got to go over to our action items application and make sure these things get entered in and followed up to make sure it gets done. I'm pretty happy with that, and we could keep going with the rest of the flasher blocks, but you get the idea. We've already updated our requirements for the power supply block, which need to be redesigned. Now, often when we do an FMEA, we have mitigations. We must add recommendations. We must perform integration tests. And we have to document this right now as part of our FMEA. And it's part of a common situation where engineering processes are quite iterative. And that's one of the reasons I really like the spreadsheet, because I could cut and paste and add rows and delete rows. And it took me some time, but that's so much better than those paper forms. One of the reasons is engineering design processes are iterative. They always are. Let's go back and look at our updated design. I've got a nice dual redundant power supply. It has two separate inputs. It has two separate conditioning circuits, transient protection circuits, and reverse polarity protection circuit. And I've added a power diagnostic to all the output voltages. If any of the power supplies, either one of the power supplies fail, I'll be able to detect each one individually. And now I've got, see, a new block, power diagnostic, and a diagnostic output circuit. So yeah, think about that for a minute. You have to enunciate a failure in order for a diagnostic to be of any value. If the flasher device knows that something has failed and it can't flash, that's not a good enunciation anyway. You've got to have a diagnostic output, an enunciation output circuit. And our new design does. Good. I like this new design. I think we're going to switch over to a tool now, because I don't know how many more iterations we're going to have to go through by the time we're all designing, but I'd rather have something that makes it easier and faster. And there are many tools available on the market right now that have different requirements and different levels of complexity. Some of them are configurable, so you can select a level of complexity. I did tell you that I used to use a spreadsheet, but I've moved over to a tool now because it saves me time, especially with the piece of it that I dislike the most, which we'll talk about in a moment. Let's use an example tool. Now, in this tool, we enter the architectural units, and there is a unit node editor, and we're going to enter it hierarchically. In this case, there's only one level. We enter the power supply block. One is enough, although it is duplicated. The LED control block, the power diagnostic block, the LED array input circuit, and diagnostic output circuit. Each one of those has functions, and we'll end up having failure modes, and then we will choose. Maybe we need more mitigations. Let's find out. We got the blocks listed. Good. Now we're going to sit down and enter the failure modes. Now that can be entered manually, but this particular tool has a automatic failure mode generator. You identify the block type, you hit the load subtree button, and pop, up comes a list of known failure modes for each block type. Perhaps you can see why I am able to save so much time. Good, now I have a list of failure modes for each of the blocks. These are predefined, supported by many years of failure analysis by a number of experts. And that's also nice because I can do an FMEDA with far less technical expertise in the room. And of course, for each one of these failure modes, you define the potential impact without mitigation. And many of them, of course, as we've already found on the power supply, are dangerous failures. I can also press a button on this particular tool to suggest mitigations. And that's really nice based on expert experience. They suggest a low voltage monitor. Well, okay, that's kind of what we have already suggested a diagnostic, and a low voltage monitor is exactly the kind we need. Among the mitigations, you choose the ones you want. We have chosen no specific mitigation for the high because we have a redundant power supply. We don't need it now. And of course, input blocking diode is a mitigation for the reverse polarity. This is nice. Now, hold it. Did we just finish the FMEA? I've got my blocks, I've got my failure modes, I've got my mitigations. Boy, we're almost finished. We also want to enter the derived design requirements and the integration tests, and this particular tool allows us to enter them directly and will generate reports that that can be integrated into other requirements tracking systems, or you can use the tool itself to track all the requirements. We have entered integration tests for the external power supply over voltage and under voltage, power surge on the external power supply, reverse polarity on the external power supply, and short circuit test of one LED. Because when we're all done, we've identified those as integration tests we want to run to verify the correctness of our FMEA. And the action item that we have is to write the proof test objective for inclusion in the safety manual. Oh, geez, I almost forgot about that. Okay, good. So in conclusion, FMEA is a very effective verification technique and can be powerful and worth all the time, whether you use a spreadsheet or an FMEA tool. The objective, to find problems early in the design process. Why? Reduces rework, and which saves money and saves development time, schedule. I don't have to repeat. Those of you who are very experienced understand the cost of rework in terms of destroying the development schedule. Time to market is not good under that situation. A spreadsheet is a traditional FMEA analysis tool. FMEA tools, however, are now on the market for many years, which help prevent errors, remind you of things to be done, reduce the engineering hours, and reduce the calendar time. Next generation FMEA tools have built-in knowledge bases with failure modes based on block type and effective mitigations. And more importantly, at least many of the tools will automatically generate the FMEA reports, the part that I really did not like doing. I hope you found this of some benefit. Think about how you use your FMEA tool. Think about how you use your spreadsheet. Do not make it overly complex. Get the job done without spending any more engineering hours than you must. This is part of our webinar series. Look at the things that are coming up. We're going to do some we're going to do a webinar on how does the instant failure modes work. We're going to be doing a webinar on keeping FMEA participants awake. I hope some of you who have experienced FMEAs smile at that statement. And then we're going to wrap it up showing you how a 2-hour FMEA can be done with a FMEA tool instead of a 2-week, 2-hour. And a lot of it is the advanced features of next generation tools. Anybody have any questions? I've got the question open. I do see one already. May we have the video? Yes. The on the first end, you will get slides, a summary set of slides, and the video will be available to watch for a period of time via the Exida website and YouTube. I expect it'll be posted on YouTube. Let me get down through any other questions right now. Yes, I see it. Now, it says OEM tool project output directly used. Well, to be specific, the OEMX FMEA tool that we were using in this example, and most FMEA tools will generate reports that directly will provide evidence for functional safety and or cybersecurity certification projects. Of course, that's where your documentation is real important if you're getting your project certified by a notified body or an accredited globally accredited body. Keep those questions coming. Would you say that DFMEA is a peer review? No, no, it's far more systematic. The common peer review is less formal, less documented, and the FMEA takes a bit more time, unless you have an instant FMEA tool. But it's not at all the same thing as most people interpret a peer review to be. Good question. I see a question, what about a process FMEA? Well, we're focused on the design right now, and that's an important point to make. You're not focused on problems outside your scope of interest. In our case, we were focused on the design of this visual enunciator, which we call the flasher. We don't worry about the power system coming from the outside world. We don't include what happens when operating instructions to describe what happens when the thing starts to flash, that stuff like that. Can it be used for chemical engineering? Well, it could be, but there are better tools. There are tools on the market that are very specifically oriented toward chemical industry, and I would call them HAZOP tools. And quite frankly, now that you asked the question, I would recommend a tool which is part of the Excellentia suite, not the OEMX suite. You gave me an opening, so Exida has a much better tool for use in chemical engineering and process engineering, and that is the Excellentia tool, specifically the PSA application. Any suggestion towards experience needed to run? When I first learned it, I was completely by myself. I did not read the instruction manual because, it's a real engineer doesn't read the instruction manual. That sounds like a sign I should have on my wall, but at that point, I contacted an experienced user who gave me a half-hour tutorial, and I was off and running. There's only a few things you need to know for the basics. Now, for the advanced features, I do recommend actually reading the instruction manual. Can FMEA used? Can FMEDA used for RAM, reliability and maintainability analysis? Absolutely. Now we did have a series of webinars on FMEDAs earlier in the April-May timeframe. And the answer is FMEDAs are valuable, but today's topic is FMEA, and it's valuable for feeding to feed information to an FMEDA. But that's another set of webinars, and I can tell you those webinars are available on the exida website, and you can go back and look at any of the FMEDA webinars. Check our time. Okay, a couple minutes are left. What's the difference between an FMEA and a HAZOP? Basically, nothing. Nothing. I find HAZOP was the older word that came from the chemical industry. It was used early on for software FMEAs, excuse me. And back then, I took a course in the 80s called Software HAZOP, and it's the exact same thing. Lately, the word HAZOP has disappeared from most of the literature, and FMEA is taken on a more universal definition. That's a good question. There's no difference. The concept are the same. They're very analogous. They both use guide words. All right. I'll scan through the questions. That looks good. Anybody that has any more questions, don't hesitate to send an email. You can use the info@exida.com. Let me just check this. Info@exida.com email address, and we'll be happy to get right back to you with your answers. Thanks very much for attending. I hope you can attend the rest of our webinars coming up later this month and 1st of November. Have a great day. Goodbye.